Welcome to the Explainer. Today, we're hosting something a little different, what we like to call the Tao Salon in statistics. It's all about finding the right path, the correct flow, for what to do after you get that first exciting result.
So here's our game plan. We'll start with the cliffhanger that ANOVA always leaves us on. Then, we're going to talk about a huge trap called the multiple comparisons problem. After that, we'll meet the heroes of our story, the post-hoc tests, understand the trade-offs they bring, and then wrap it all up with some really practical takeaways for your own work.
All right, so picture this. You've run your big analysis, you're looking at the results, and bam, it's significant. You've found a difference between your groups. It's a great moment for sure, but it also leaves you hanging with a massive and kind of frustrating question.
So, an ANOVA, which stands for Analysis of Variance, is an absolutely fantastic tool. The best way to think about it is like a smoke alarm for your data. It's amazing at telling you, hey, there's a fire somewhere in the house. But it doesn't tell you which room is on fire. It just screams that a difference exists somewhere.
See, when your ANOVA gives you that nice, small p-value, it means you can confidently say that not all your groups are the same. You accept this alternative hypothesis, which basically says, okay, at least one of these groups is the odd one out. But which one? Is it group A that's different from B, or is C way different from everyone else? The ANOVA just shrugs. It doesn't tell you.
And that, right there, is our cliffhanger. We have a mystery on our hands. Now, your gut instinct might be to just, start comparing every group to every other group. Run a test for A versus B, then A versus C, then B versus C, and so on. But here's the kicker. That totally logical next step is actually a huge statistical trap.
This brings us to something absolutely critical in statistics called the multiple comparisons problem. Here's the bottom line. The more questions you ask your data, the higher the chance your data is going to lie to you just by random luck.
To make this super clear, let's use an analogy. Let's talk about dice. Imagine you've got a 20-sided die, and your only goal is to roll a 1. With just one roll, your chances are pretty slim, right? Only 5%. But what happens if you just keep rolling more and more dice?
Well, your odds start to look suspiciously good. With just 5 dice, your chance of seeing at least one 1 shoots up to over 22%. It's the exact same thing with statistical tests. If your significance level is 5%, every single test you run has a 5% chance of giving you a false positive. That is, finding a difference that isn't actually there. The more tests you run, the more you're just rolling the dice, hoping to get lucky.
This ballooning risk has a proper name, the family-wise error rate. It's the total probability of making at least one of these false positive mistakes across the entire family of tests you run. And as you're about to see, this thing gets out of control fast.
Just look at this table. This is what's so wild. It shows you just how fast this error rate climbs. If you have 6 groups you want to compare, that means you have to run 15 different comparisons. And at that point, your family-wise error rate is over 50%. That means you have a better than a coin flip chance that at least one of your significant findings is total garbage. It makes your results completely unreliable.
So if we can't just run a bunch of separate tests, what are we supposed to do? How do we investigate properly? Well, this is when we call in the specialists. Post-hoc tests. Post-hoc just means after this, and these tests are specifically designed to jump in after you get a significant ANOVA, find out where the real differences are, and do it all while keeping that crazy family-wise error rate under control.
You can think of these like different kinds of detectives you can call on. Tukey's test is your all-rounder, your workhorse. It compares every single group to every other group. Holmes' method is the really cautious detective. It's a bit more conservative, so it's less likely to point a finger. And then there's Dunnett's. That's the specialist you call when you have a control group, and you really only care about comparing your new treatments back to that one baseline.
So this is the whole game right here, choosing the right tool for the job. And it all depends on the question you're trying to answer. If you've got 3 new marketing campaigns, A, B, and C, and you just want to know which one is the best overall, you use Tukey's. It'll compare all of them. But if campaign A is your tried and true current campaign, and B and C are new challengers, you use Dunnett's. It focuses the investigation only on the questions that actually matter. Is B better than A? And is C better than A?
Okay, so these specialized tools are amazing, but they're not magic. Using them comes with a built-in trade-off, and it's kind of like a classic investigator's dilemma.
The benefit is super clear, right? By being stricter, post-hoc tests protect us from those embarrassing false positives. We get precision. But the cost is a little less statistical power. And power is just the ability of your test to find a real difference if there actually is one. So by being extra careful not to wrongly convict an innocent group, we slightly raise our chances of letting a guilty one get away. It's a balancing act.
So how do you handle this? The secret is planning. You have to think like a detective before you even start the investigation. Before you even run that first ANOVA, decide which comparisons are the most important for your question. By focusing your analysis from the start, say by deciding you only need Dunet's test, not the whole shebang with Tukey's, you don't have to give up nearly as much power. It's about being strategic.
Okay, let's bring this all home. Let's talk about how all of this stuff actually applies in the real world, whether you're in marketing, business, or doing consumer research.
You know, we can really boil all of this down to 3 core ideas, 3 key conceptions that will help you make way smarter decisions with your data.
First, find the real winner. When you're running a test with, say, 3 different versions of an ad, an ANOVA might tell you, yep, they're not all the same, but it's the post-hoc test that lets you confidently point to one and say, that's the one. That's our true statistical leader, not just the one that got lucky that day.
Second, avoid false discoveries. This is all about managing risk. By controlling that family-wise error rate, you stop your company from chasing statistical ghosts. You avoid that incredibly costly mistake of pouring time and money into a new product or a big campaign based on a finding that was really just a fluke.
And finally, number 3, use the right tool for the job. This is all about being efficient and getting clear answers. When you know ahead of time if you need to compare everything to everything or just everything to a baseline, it streamlines your whole process. It makes you clarify your question from the get-go, which always leads to a faster, more direct conclusion.
So the next time your ANOVA pops up and tells you, hey, there is a difference in here somewhere, you'll know that's not the end of the story. It's really just the beginning of the investigation. And now you'll have the right tools to find out what's really going on and to answer the most important question of all. Are your conclusions based on a real difference, or did you just get a lucky roll of the dice?